welcome to Senior Advanced Session 1. Today we're going to be discussing exponents and logarithms. For the purposes of this lecture, we're going to assume that you've already read the lecture notes. However, in case you didn't understand everything, let's go over the lecture notes in a bit more detail now. So we see exponents written as x and then a superscript y. Now these aren't always one number, sometimes they're expressions, but in general, this means that x is multiplied by itself y times. If x was 3 and y was 4, we multiply 3 by itself 4 times. 3 times 3 times 3 times 3 equals 81. So 3 to the 4th power equals 81. In an exponent, x is called the base and y is called the exponent, or the power. However, after we've defined the positive integer exponent, we have to ask, what about a negative exponent? What would we get if we wrote 3 to the negative 4th power? As it turns out, we define x to the negative y as being equal to 1 over x to the y. So, since we know that 3 to the 4 is 81, we know that 3 to the negative 4 is 1 over 81. Okay, so if our goal is defining the exponent function for all integers, we've covered all positive integers, we've covered all negative integers, but what about 0? Now, in order to figure out what a number to the 0 power is, we're going to have to look at the pattern exponents make. Let's look at this chart. You'll notice that these are all of the powers of 3. 3 to the negative 3rd power is 1 over 27. 3 squared is 9. You'll notice that when we're moving between the powers of 3, we have to multiply by 3 to move to the right. 1/27 times 3 is 1/9. 3 times 3 is 9. And when we want to move to the left, we have to divide by 3. 1/3 divided by 3 is 1/9. 27 divided by 3 is 9. So let's look at the missing number. We have to figure out what 3 divided by 3 is. Is it the same as 1/3 times 3? Yes, it is. This missing number is 1. Thus, we can conclude that 3 to the 0 power is 1. As a matter of fact, this is true for all numbers. X to the 0 equals 1, as long as x does not equal 0. Our next topic is exponent rules. These are basically rules that'll let you manipulate exponents and help you simplify expressions and solve equations. Our first rule is that a to the x times a to the y equals a to the x times y. For example, 3 squared times 3 to the 5th power equals 3 to the 2 plus 5 power, which is 7. Our next rule is useful when you have exponents with similar bases on the numerator and the denominator of the same fraction. A to the x divided by a to the y equals a to the x minus y. In this example, we have 3 squared divided by 3 to the 5th power. This is equal to 3 to the 2 minus 5 equals negative 3 power. However, we never use negative exponents when expressing our answers. So, to further simplify this, we must write it as 1 over 3 to the 3rd power. Our next rule is that a to the x, all to the yth power, is a to the xy. Remember, x needs to be inside of the parentheses, while y is outside the parentheses. From this, we can also conclude that ax to the y is the same as a to the y to the x, because they are both equal to a xy. For example, 3 squared to the 3rd power equals 3 to the 6th power. But we can also conclude that 3 squared to the 3rd power equals 3 cubed to the 2nd power. So we have 9 cubed equals 27 squared. Our next topic is fractional exponents and roots. This is where the lecture gets a lot more complicated and a lot more fun. So instead of looking at basic integer exponents, we're going to be looking at exponents like this. 3 to the 2/5 power. And we're also going to be looking at radicals, like the 5th root of 8. Don't worry if you don't understand any of that now, because you'll understand that as soon as you watch this portion of the lecture. You've probably seen this symbol before at some point. This is the yth root of x. In this radical, the whole thing is called the radical, x is called the radicand, y is called the index, and this sign here is a radical sign. If no index is specified, we can assume that the index is 2. Now, saying that the y-th root of x equals a is the same as saying a to the y-th power equals x. So, when we ask what the y-th root of x is, we're really asking what 1 raised to the y-th power will give us x. Here's an example. The cube root of 8. What we're really asking here is what 1 raised to the 3rd power will yield 8. Well, we know of one such number, 2, because 2 to the 3rd power equals 8. You might be wondering why I'm teaching you about roots, because roots don't really seem to have much to do with exponents. However, there's an important relationship between roots and exponents. 8 to the 1/3 power is equal to the cube root of 8, where 3 is the index. If it's 1 over x, then x will be the index. Let's look at another example. 16 to the 1/2 power. Well, 16 to the 1/2 power is just the same as writing the square root of 16. Remember, when there's no index, the index is equal to 2. So, we know what the square root of 16 is. The square root of 16 is 4. What about fractional exponents that aren't inverses of integers, like 8 to the 2/3 power? Well, we can split the exponent apart. Since 2 times 1/3 equals 2/3, we know that 8 squared all to the 3rd power is equal to 8 to the 2/3 power. Converting the 1/3 power to a root, we get that 8 to the 2/3 power is equal to the cube root of 8 squared. Then we get that 8 to the 2/3 power is equal to the cube root of 64. But what if you didn't know the cube root of 64 off the top of your head? Well, let's look at another way we can solve this problem. As we discussed earlier, if this is true, this must also be true. If 8 squared to the 1/3 power is equal to 8 to the 2/3 power, then 8 to the 1/3 power, all squared, must also be equal to 8 to the 2/3 power. Then, we convert 1/3 into a root. So we have that 8 to the 2/3 power is equal to the cube root of 8 squared. We remember that the cube root of 8 is 2. So we have 8 to the 2/3 power equals 2 squared. And we all know what 2 squared is. 4. When converting fractional exponents into roots, we have the choice of either writing the exponent on the outside of the radical sign or the inside. Now these two expressions are equal to each other. However, arbitrary mathematical notation dictates that we have to put the exponent on the inside. So don't write your answers like this, write your answers like this. There's no real reason for it other than that it's easier to read, and that's what the standard is. Let's check your progress. Pause the video now and try to evaluate 25 to the 3/2 power. Did you get the answer as 125? If you did, you probably have a good understanding of the concept. If not, you should probably go and rewatch this section of the lecture. We have to rationalize denominators because in the 1600s, when they were beginning to invent math, they didn't have calculators. So, they didn't want to divide by irrational numbers by hand because that was really difficult. So, they made the standard that we have to rationalize our denominators, basically saying that we can't have irrational numbers in our denominators. So, we're going to teach you how to get rid of irrational numbers in the denominator. Before we can understand rationalizing denominators, we need to understand the concept of a conjugate. Let's consider 3 plus the square root of 5. What would the conjugate of this be? Well, we have to take the rational part of the number and subtract the irrational part. That's all there is to it. Consider this expression. If you're solving a problem and you get this as your answer, you're not allowed to write this as your answer because there's an irrational number in the denominator. Let's look at how we can rewrite this expression without an irrational number in the denominator. We are going to employ a seemingly trivial principle that 1 equals x over x. Since this is an expression and we need the final value to be equal to the original value, the only thing we can do is multiply it by 1. However, since x over x equals 1, we can also multiply it by the conjugate of the denominator over the conjugate of the denominator. Let's multiply this out and see what we get. The numerator times the numerator is 2 times 4 plus rad 7. And the denominator times the denominator is 4 minus rad 7 times 4 plus rad 7. But if you look at this closely, you'll notice that this is in the difference of two squares format, where 4 being x and 7 being y, x plus y times x minus y. Now we know that in the difference of squares, x plus y times x minus y equals x squared minus y squared. So we get our denominator as x squared, which is 4 squared, which is 16, minus y squared, which is 7. So our denominator is 16 minus 7. Now, we distribute the 2 into the 4 plus rad 7 to get a numerator, 8 plus 2 rad 7. You'll notice I wrote 2 right next to the radical sign. When you want to write an integer or a coefficient multiplied by a radical, you just write it right up next to the radical, like I did with 2 and rad 7. So we have our answer, 8 plus 2 rad 7 over 9. Consider this problem. We don't have 2 terms in the denominator, so we can't simply make a conjugate like we did last time. We need to only have one irrational term in the denominator in order to employ the process we did last time. So we're going to have to get a little bit creative. We have to group the second 2 terms or the first 2 terms as one term. So we multiply by the slightly modified conjugate where we only replace this specific sign. We're going to end up with another difference of squares formula that will eliminate the radical 5. As you can see, we've multiplied out the bottom. Since we had rad 5 and rad 2 plus 1, we have 5 minus rad 2 plus 1 squared. Let's simplify rad 2 plus 1 squared. We get 5 minus 3 plus 2 rad 2 in the denominator. You'll notice now that there's only one irrational term in the denominator. We can now simplify the denominator and repeat the process. Here is the fully simplified denominator with only one irrational term. Again, we multiply the top and bottom by the conjugate of the denominator, 2 plus 2 rad 2. We reapply the difference of squares formula. 2 squared, which is 4, minus 2 rad 2 squared, which is 8. 4 minus 8 is negative 4, which is our new denominator. Multiplying out the numerator, we get the following. We can simplify further by combining like terms. We realize that there is a factor of 2 present in both the numerator and the denominator. So we cancel out this factor of 2 and simplify. We get this as our final answer. 3 plus 2 rad 2 minus rad 5 minus rad 10 all over 2. If you want, you can plug this expression into a calculator as well as plugging the original expression into a calculator, and you will see that both expressions have the same decimal expansion. The last type of problem you will encounter in this class is where there are radicals whose index is not 2 in the denominator. Now, if the radicals do not have an index of 2, we will not ask you to solve equations like this, where there are multiple terms in the denominator. However, they're still difficult to solve, so let's learn to solve them. We can think of these as powers of 2 and 3, fractional powers, 3 to the 2 thirds and 2 to the 3 fifths. However, we need 2 and 3 each to be raised to an integer power in order to be rational. Let's figure out how we can do that. First, what can we multiply the top and bottom by? Well, let's look at 3 first. 3 is raised to the 2 thirds power. We need to get it to 1. When you multiply 2 exponential expressions with the same base, you add their powers. For example, 3 squared times 3 cubed equals 3 to the 5th power. Well, we just have to modify this expression. We want the answer to be 3 to the 1st power, or 3. One of them is 3 to the 2 thirds. Thus, the other one must be 1 minus 2 thirds is 1 third. Let's try multiplying the top and bottom by 3 to the 1/3 power. We end up with this expression. 3 to the 1/3 power over 3 times 2 to the 3/5. Alright, so we've eliminated one of the irrational numbers in the denominator. Let's try to repeat the process for 2. Alright, we have to figure out 3 over 5 plus what equals 1? Well, the answer is clearly 2 over 5. So let's multiply the top and the bottom by 2 to the 2 over 5 power. Here is our result. Let's convert the fractional exponents back into roots and multiply out the denominator to get our final answer. And here we have our final answer. Keep in mind that the 5th root of 4 is from having the 5th root of 2 squared. And in our final answer, we have to simplify 2 squared to 4. Our next topic is going to be logarithms. Consider a to the x equals b. At this point, I'm going to assume you have a pretty good grasp of what exponents are, so you should understand the meaning of this expression. Say we know the value of a, 5, and the value of x, 8, but we want to express the value of b. How would we express the value of b? Well, we would simply write 5 to the 8th power. But what if we know the value of b and we know the value of x, but we don't know the value of a? Well, in this case, we would write the xth root of b. In this case, since x is 8 and b is 7, a would be the 8th root of 7. The next question logically is, how do we write x in terms of a and b? Well, this is what we use the logarithm function for. What we're really asking is, if a is 3 and b is 5, 3 to what power equals 5? We log base whatever's getting raised to the power, which in this case is a, which is 3, of the resulting power that we want, which in this case is 5, is equal to the power you need to raise this base to get to the thing inside of the parentheses. On the board, you see the expression log base 3 of 9 equals blank. So, we're going to figure out what log base 3 of 9 is. What this is really asking is 3 to what power equals 9? Well, we already know that 3 squared equals 9. Thus, log base 3 of 9 must equal 2. Logarithm rules are going to help you evaluate expressions like log base 81 of 1 over the square root of 3. You probably don't know off the top of your head what power we have to raise 81 to in order to get this 1 over the square root of 3. In order to figure that out, you're going to have to use logarithm rules. The first exponent rule is that log base b of x to the nth power is the same as n log base b of x. The square root of 3 is 3 to the half power. 1 over the square root of 3 is thus 3 to the negative 1/2 power. So we know that log base 81 of 1 over the square root of 3 equals log base 81 of 3 to the negative half power, which is equal to negative 1/2 times log base 81 of 3. Our next logarithm rule, which will help us simplify this expression further, is log base b of a equals log base c of a over log base c of b, where c is anything as long as it's positive. Why does c have to be positive? Well, this is called the base of an exponent, and this is called the argument of an exponent. Both the base and the argument must be positive, or the logarithm is not defined. We can employ this rule to get that log base 81 of 3 is the same as log base 3 of 3 over log base 3 of 81. Our next rule is that log base a of a equals 1. Thus, we can simplify log base 3 of 3 to 1 to get that the new expression is negative 1/2 times 1 over log base 3 of 81. Since we know that 3 to the 4th power equals 81, we know that log base 3 of 81 is 4. Thus, we can substitute 4 in for in the expression and get that log base 81 of 1 over rad 3 equals negative 1/8. This is the same as saying that if we raise 81 to the negative 1/8 power, then we will get 1 over rad 3. In addition to those rules, we have 4 more. 1. Log base a of 1 equals 0 for all valid a. This is because a raised to the 0 power will always be 1. 2. When you switch the base in the argument of a logarithm, you get the inverse of the original logarithm. 3. Log base a of the product of two numbers is equal to the sum of log base a of the two numbers. And lastly, log base a of m over n equals log base a of m minus log base a of n. To check your progress, please try this example problem. If you're having trouble, just rewatch the example problem that I did. Then, try to apply the same method to solve this problem. Did you get the answer equals 2/9? If you didn't, and you are not sure why you got it wrong, please review this section of the lecture. The lecture so far has been pretty slow. That's because we're just reviewing what was already written in the lecture notes. You've already read through this material. However, at this point, we are going beyond what the lecture note specifies. We're going to be talking about solving equations using exponents and logarithms, and all of the tips and tricks you can use to help yourself solve these equations and inequalities. Now, most of the classwork and homework is going to be based on this section. The only reason we spent so long on the previous sections is because, well, you have to understand those concepts in order to understand this section. But you need to pay really close attention to this section, or you're not going to understand all the problems in the classwork or the homework. This is our next topic. It's called equating exponents. This principle basically states that if the base is same on both sides, then the exponents must equal each other. If 2x, or if 2 to the x power, equals 2 squared, then x must equal 2. Let's look at a problem involving this. Take a look at this example. 2 to the x squared equals 2 to the 5x minus 6. We'd simply equate x squared with 5x minus 6. This leaves us with a simple, easy to solve quadratic. It's important to note that you cannot equate the two exponents if the bases are not equal. So what do we do in this case? Well, since 8 is a power of 2, we can change it into 2 to the third power. Thus, the exponent on this side is 3x squared because we multiplied 3 by the x squared. So this time we would equate 3x squared with 5x minus 6, leaving us with yet another quadratic equation. Similarly, a equals b if log a equals log b and the two logarithms have the same base. But wait, these two logarithms don't have bases at all. What does that mean? Well, when no base is present, we can assume that the base is 10. You might also see logarithms that have base e. E is a transcendental number we'll learn about later. For now, just know where it is on your calculator. However, we don't write log base e. Rather, we convert it to ln. Saying ln of a is the same as saying log base e of a. It's called a natural logarithm. Next, we're going to cover using logarithm rules in reverse in order to solve equations. So, the first thing we're going to do is pull this 3 inside and make it an exponent of x. The next thing we're going to do is use the definition of logarithms to convert this 3 into a logarithm. So we have to figure out log, base 10 because there's no base listed, of what is going to be 3. Well, 10 to the third power is 1,000. Thus, 3 is equal to log base 10 of 1,000. Sorry, the writing's getting a little squished, but the next step is to convert both sides into one logarithm using the subtraction rule. Now, the two bases of the logarithms are the same, so we can equate the arguments of each side of the equation. Then, we have an equation that does not have any logarithms in it, which we can solve to get x equals 10 times the cube root of 9. Though you won't need it often, there will be one problem on the classwork where you're required to convert an exponential form like this, a to the y is greater than x, to logarithmic form. This means that y is greater than log base a of x. This is because x is actually equal to a to the log a of x. But if if this side is greater than this side, and they have the same base, then that means the exponent on this side must be greater. So y is greater than log base a of x. You may be wondering how I knew that a to the log base a of x would equal x. Well, log base a of x, by definition, is the power you need to raise a to in order to get to x. So if we're raising a to the power we need to raise it to get to x, we're going to get x. I know that sounds like a lot of words, but in the end, it's a simple concept. Now we're going to learn about simplifying roots. Consider the cube root of 16. This may look like it's fully simplified, and it's true. There's no whole number that when cubed equals 16, but we can simplify it. Here's how. The first step is to decompose the radicand, the number under the radical sign, into its prime factors. The prime factors of 16 are 2 times 2 times 2 times 2. Then we look at the index, this number right here. This number is 3. So we look and we see for any groups of 3 of the same prime factor. There's one group of 3 of the same prime factor. There are 3 2's. We pull out the factor and multiply the radical by the factor. This gives us our final answer. If there are any groups of 3 factors still inside of the radical, then the radical is considered unsimplified. This is Will. He is 10 years old, and he is going to demonstrate how to take the square root of 180.
Here, there is no number here, so we know it must be a 2 for the index, or it means that it must be the square root. Next, we're going to look at the prime factors of 180. They are 2 times 2 times 3 times 3 times 5. Next, we're going to look for groups of 2. Here we have 2 2's and 2 3's. Now we're going to pull the groups out of the radical and put them into the coefficient. Now here's our answer, 6 rad 5. If I can do it, you can do it.
The last topic of the day is modeling. It's quite a quick topic too. All I'm going to do is show you how to make predictions about the real world using exponential equations. Okay, let's look at a quick example. We have 30 cells in a petri dish. They triple every hour, and we need to find a function of t time that's going to tell us how many cells are in the petri dish at any given time. How we're going to do this is we're going to start off with 30 cells. After 1 hour at t equals 1, we're going to multiply it by 3. At t equals 2, we're going to multiply it by 3 squared. By t equals 3, we're going to multiply it by 3 a third time and make this 3 to the third power. You may see a pattern emerging. We multiply it by 3 t times. So, at the third hour, we'll have 30 times 27 cells in our petri dish. This is our function. F of t equals 30 times 3 to the t. This is the basic layout of every single modeling function you're going to do. An original value times an exponential value to the number of t's it takes for that exponential to occur. If it tripled every 2 hours, we would have 3 to the half t. Because it's only going to triple half of the number of the t. Like if t were equal to 4, it would only triple 2 times. So we have to have that. And this concludes today's lecture, Session 1, Senior Advanced. My name is Charlie, and if you have any questions, you can email me at charlie.nix@agoramathcircle.org. Or, if you're not in the online class, you could show up 30 minutes before class starts at 1:30, and you can ask questions about the lecture then.
Don't forget to subscribe and like. If you have any questions, you can email info@agouramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!